Good morning, everyone. Welcome to today's presentation. I'm excited to introduce our topic, the impact of the Charpy Impact Test. In this session, we'll explore how this test helps us understand material toughness under sudden loads. We'll also look at how it differentiates between ductile and brittle behaviors, which is crucial for ensuring structural safety. So let's get started and see what this important testing method is all about. Today, I want to talk about the critical standards that guide our testing processes. First, we have the Indian standard, IS 1757, which sets the specific requirements and procedures relevant to our local testing practices. Then, there's the ASTM standard, ASTM E23, a widely recognized benchmark used internationally, especially in the United States, for its rigorous testing methods. Lastly, we have the ISO standard, ISO 148, which provides a global framework for testing that ensures consistency and comparability across different regions. These standards are essential because they ensure that our testing is accurate, reliable, and consistent, regardless of where we're conducting our tests. By adhering to these established guidelines, we can confidently compare results, maintain quality, and meet industry expectations. Connecting this to our overall theme, understanding and applying these standards is fundamental to ensuring the integrity and credibility of our testing processes, ultimately supporting the quality we deliver. Let's talk about the principle of the Charpy test. Essentially, this test measures the energy absorbed when a notched specimen fractures. The specimen is supported at both ends, creating a simple setup. A pendulum is released from a known height, which gives it a specific amount of potential energy. When the pendulum strikes the specimen, it breaks. The key idea here is that the energy absorbed by the specimen is equal to the difference in the pendulum's height before and after the impact. This energy absorbed tells us a lot about the material's toughness. If a material absorbs a lot of energy before breaking, it's considered tough. Conversely, if it absorbs less energy, it tends to be more brittle. We measure this energy in joules, and it helps us classify materials based on their fracture behavior, whether they are tough or brittle. So, by understanding the energy absorption, we get valuable insights into the material's ability to withstand impact without fracturing. Let's take a closer look at the standard specimen size, which is typically 55 millimeters long, 10 millimeters wide, and 10 millimeters thick. Keep in mind that the thickness can vary depending on the material we're testing. Now, moving on to the types of notches, the most common one you'll encounter is the V-notch, but there's also the U-notch. For the typical V-notch, it usually has a depth of about 2 millimeters, an angle of 45 degrees, and a root radius of 0.25 millimeters. These dimensions are important because they influence how stress concentrates around the notch during testing. As for the U-notch, it generally has a notch depth of 5 millimeters, a radius of about 1 millimeter, and a rounded, semicircular profile. The U-notch's shape distributes stress differently compared to the V-notch, which can be useful depending on the specific material and testing requirements. Understanding these dimensions and types is crucial because they directly impact the test results and help us evaluate material toughness consistently. So, when selecting a specimen, pay close attention to these details to ensure accurate and reliable measurements. Let's talk about the purpose of a notch in material testing. The main idea here is that a notch creates stress concentration. This means it directs the stress to a specific area, making it easier to study how cracks might initiate. By doing this, we can simulate the beginning stages of crack formation under real-world conditions. This is particularly useful because it helps us evaluate how materials behave when they are brittle. Brittle materials tend to fracture suddenly, so understanding where and how cracks start is crucial. Overall, the notch is a simple but powerful tool that allows us to better predict and analyze material failure, linking directly to our goal of improving material reliability and safety. Now, let's take a look at how materials behave under different temperature conditions. We test at room temperature, sub-zero temperatures, and elevated temperatures to see how they respond. Each of these environments can significantly influence the material's fracture behavior. For example, at high temperatures, materials tend to undergo ductile fracture, meaning they deform more before breaking. Conversely, at low temperatures, materials are more prone to brittle fracture, which happens suddenly with little deformation. Understanding these effects is crucial because it helps us predict how materials will perform in various environments, ensuring safety and reliability in their applications. This connection between temperature and fracture mode is a key part of the overall theme of material performance and durability. All right, let's walk through the testing procedure. First, you want to mount the pendulum at a specific height, making sure it's secure and stable. Then, take your notched specimen and place it horizontally at the bottom of the setup. It's important to position the notch so that it faces away from the striker. This ensures the impact occurs precisely where you want it to. Next, release the pendulum freely. Gravity will do the work. When it swings and hits the specimen, it will break or fracture the material at the notch. After the fracture, you'll want to carefully note the energy absorbed during this process. This absorbed energy is crucial because it indicates the material's toughness and ability to withstand impact. This procedure is a key part of understanding how materials behave under sudden forces, and it directly connects to our overall goal of assessing material toughness and reliability. Remember, precise setup and accurate measurements are essential for meaningful results. Let's take a moment to understand this concept more clearly by watching the video. As you watch, pay close attention to the key points being demonstrated. This will help solidify your understanding of how these ideas come together in a practical way. Remember, the main goal here is to see the real-world application of what we've been discussing so far. This visual will connect the dots and make the theoretical concepts more tangible. So, keep your focus, and let's see how these principles play out in action.
First, raise and secure the pendulum in its initial position. Set the dial indicator to 300. Place the specimen on the anvils, ensuring that the notch faces away from the pendulum. Release the pendulum to strike and break the specimen. Observe and record the absorbed energy indicated on the dial, that is 150 joule here. After the test, bring the pendulum to rest using the brake.
Now let's talk about lateral expansion. This refers to the increase in the width of the specimen at the notch root after it fractures during impact testing. Essentially, when the material breaks, it often bulges outward, and this outward bulging is what we call lateral expansion. It's an important measure because it shows us how the material deforms under stress. We measure this expansion using a device called the lateral expansion gauge, which gives us precise readings of how much the specimen has expanded sideways. So what does this tell us? Well, a higher lateral expansion indicates that the material is behaving in a more ductile manner. That means it can absorb more energy and deform plastically before breaking. On the other hand, a lower lateral expansion suggests a brittle behavior, where the material fractures with minimal deformation. Understanding lateral expansion helps us assess the toughness and ductility of materials, which is crucial when we're considering how they will perform under real-world impact conditions. It connects directly to the overall theme of material behavior, whether a material is likely to bend and stretch or snap suddenly. Now let's talk about shear fracture. Shear fracture is quite interesting because it actually indicates that the material is tough. In other words, it can absorb a significant amount of impact energy before it finally fails. This is a good sign of durability. We usually measure shear fracture in percentage, and we determine this by comparing it with the chart provided in the test standards. Next, let's look at the fracture appearance. When a material fractures, the way it looks can tell us a lot about its properties. For example, a ductile fracture appears fibrous, which shows that the material has absorbed a high amount of energy before breaking. This fibrous look is a sign of toughness. On the other hand, a brittle fracture appears granular, indicating that the material didn't absorb much energy and broke more suddenly. Recognizing these different appearances helps us understand the material's behavior under stress and how it might perform in real-world applications. Let's take a closer look at how we report the results of impact testing. First, specimen size is a critical factor because it can influence the energy absorption during the test. Larger or smaller specimens might respond differently, so it's essential to specify the size used. Next, the type of notch applied to the specimen is key, as it creates a stress concentration point that simulates real-world flaws or cracks. The notch type can significantly affect the impact energy measured. Moving on, the test temperature is another vital parameter. Materials can behave quite differently at various temperatures, especially in cryogenic or elevated conditions, so documenting this helps interpret the results accurately. The core outcome we're interested in is impact energy, measured in joules. This value indicates the material's toughness, how well it can absorb energy before fracturing. Overall, these factors, specimen size, notch type, temperature, are interconnected and together paint a complete picture of the material's impact performance. When reporting, clarity about these parameters ensures our results are meaningful and comparable across different tests and studies. Thank you for watching. I truly appreciate your time and attention throughout this presentation. I hope you found the information insightful and useful for your own work or projects. Remember, the key takeaways are about understanding the core concepts we've covered and how they connect to the bigger picture. Whether it's the strategies, techniques, or ideas we've discussed, I encourage you to think about how you can apply them in your own context. Again, thank you for being such an engaged audience. I look forward to seeing how you put these concepts into action.